Okay, and this is the last part of the tutorial. So we've got regularization to cover next, and we're going to take a look at one versus all and multi-class classification, classification accuracy, and finally we end up with Bayesian decision theory. Okay, so this is towards the end of week 3 practice problems. So we've got regularization to deal with, and I'll talk about that in a little bit. Basically, the algorithm in terms of gradient descent and regularization is the same. If you recall, there's some slight differences, but if you call the cost function, so you have the first initial points here, this is just the regular sum of squared differences, and then you also are applying what's known as regularization on the parameters, except for the bias. You don't apply regularization on the bias, because that contributes most in terms of the accuracy of the classifier, or the predictor. So you're going from 1 to n, so everything without the bias, and then that's what the cost function is. And then when you compute the gradient descent update, the bias has just no regularization and everything else does. Okay, so let's just go ahead and do this. So we have some training. We have a training data set with just one feature. So we have 4 points, expected outputs. And what we want to do is we want to add quadratic and cubic features. So the first task is to fill out this table. The next task is to normalize the features so that you have zero mean and unit variance. I'm just going to write out what they are for you. Like I've done it often enough so you can see how it's done. And then you're going to apply gradient descent with lambda as 0.5, the regularization. You have 2 iterations. Initial parameters are 0 with a learning rate of 0.1. And then you'll apply it again when lambda is equal to 50. And then you're going to check out what the parameters look like. Okay, so I'm pretty sure I have that table somewhere. Yeah, here we go. So this is it. So this is a regularization. Okay. So we have a learning rate of 0.1. We want to compute n is equal to 2 iterations. And then the regularization parameter was 0.5, as well as the initial parameters are all equal to 0. So we have 3 features plus the bias. So our job now is to fill out the table. So the table's pretty easy. All you have to do is just do 1, 4, 8, and 27. So you're just taking the features, just squaring them, and then you do the same thing for the cubes. So 2 cubed is 8, 3 cubed is 27, and finally 4 cubed is 64. Okay, so before we even go into this, let's recall what the algorithm is for regularization. Okay. So it's basically the gradient descent update is the same, but there are some differences in terms of the rule that you use to update the parameters. So gradient descent update is the same, but rule is different. Okay, so basically, if you remember, the update is simply, so you're finding the summation of the differences between the expected values and the predicted values for the jth feature. Okay. And then you also add a regularization term. Okay? And this is for j equals 1 to up to n. There's no regularization for the bias. So I'm just going to copy this again. And this is theta 0. Okay. No regularization done on the bias. Okay, so that's what it is here. Also, the cost function may be fruitful to know. So it's the same as before. I forget the with an additional parameterization, not parameterization, regularization, plus lambda over 2m. Okay, so that's the regularization there. You can totally do this by linear algebra if you so desire. It's quite easy to do. Okay, so the update basically looks like this. And okay, so there's no regularization term applied to the bias term, but everything else does. And then this update still remains the same. Okay. Now, you would do g of x if logistic regression. But we're not doing logistic regression here. We're doing linear regression. Okay? So that's pretty much the only difference. Alright. And also, if you want to compute the cost in a linear algebra viewpoint, it's quite easy. The first term is the same as before. Okay? And then you have an additional regularization term. So, yes. So what we do here is, we'll have to do this. So we do theta 0. So you have 0, theta 1, theta 2, up to theta n. And then you multiply this with 0, theta 1, theta 2. So you don't actually compute the, there's no bias for the there's no regularization of the bias. So this will compute the sum of squares, excluding the bias term. So actually what you can do is you can just do that. You know, just make it easy. Okay. There, you just do that. Okay. Cool. Okay, and x being the x's and y are the data matrices as before, so I'm not going to write those down. But yeah, so that's how you do it, linear algebra viewpoint. So this is the rule. Okay, so what we're going to do now is we're going to calculate the mean and standard deviation for each of the features. And that's already been done. So let me just, so normalize features. Okay, so let's compute the mean and standard deviation for each feature. I've already done that for you, so I'm not going to show you the calculations because you can certainly do that on your own. So this is 2.5, 7.5, and 25. Okay, standard deviations are 1.2909, 6.5574, and 28.2252. Okay, and then what you need to do now, normalize features, so you have this, and then finally the new data set. So we have the output here, but we don't normalize those features, those outputs. So you get minus 1.1619, minus 0.3873, 0.3873, 1.1619. Okay, and this is minus 0.9912, minus 0.5337, 0.2287, 1.2962, and this is minus 0.8503, minus 0.6023, 0.6708, finally 1.3817. And also the features are the output is 1, 3.5, 9.5, and 15. So these are the new features, but the output remains the same. Okay, so now that you have this data, we're going to go ahead and compute gradient descent. We're just gonna do it for 2 iterations. Okay, so here's iteration 1. Okay, so theta 0, and there's only 4 terms, so we have 1 minus, finally 1 minus. Okay, then alpha over m. Alpha in this case was 0.1. This is equal to 4. There's only 4 training examples. Now we have to compute X transpose. Okay, so let me just write this in. I'll just switch them because just to be consistent. Okay, so this is X transpose. So you have 1, 1, 1, 1, minus 1.1619, minus 3.3873, 0.3873, and 1.1619. Then minus 0.9912, minus 0.5337, 0.2287, 1.2962. Then finally is minus 0.8503, minus 0.6023, 0.6708, and 1.3817. So this here, X transpose, that's theta. Okay, and then I gotta bring this all the way over because I'm running out of room. So this is multiplied by, right? We have the original data matrix, which is 1, 1, 1, 1, minus 1.1619. Let's see here. Yep, minus 0.3873, 0.3873, 1.1619. Just copy, just making the transpose. Okay, and then finally minus 0.8503, minus 0.6023, 0.6708, 1.3817. Okay. You multiply this by the 0 vector, and finally subtract this with the expected y. 1, 3.5, 9.5, 15. Okay, so you know this product between this and this vector is zeros. They're all zeros. Okay, so what's left now is to compute following. Also, these thetas are all zeros as well, right? Because those are all initial. So finally, what you simply have to do now is this update. So the initial vectors were 0, so you have minus 0.1 over 4, and then we're going to take our X transpose matrix, which is up here. transpose. So now minus 1, minus 3.5, minus 9.5, minus 15. Okay, when you do this computation, I won't spoil it for you, but when you finally do this, we get 0.725, 0.4648, 0.4689, and 0.4610. Inputting some relevant information. Okay, so that's the first update. Also, I'll let you compute the cost function on your own, but it's basically 22.9365. Okay. Alright. So, let's see. Okay, let's do the next iteration. Okay, so we have, the bias term stays the same, and now what's going to happen is we apply regularization. So 1 minus alpha lambda, which is 0.5 over m, times the previous parameter, which is 0.4648. Okay, remember, this is alpha, this is lambda, this is m. Okay, and now we have to just repeat this for the rest of the parameters that we have. And the previous one was 0.4689, 1 minus 0.1, 0.4610. Okay, so that's the vector there. And then we'll do minus 0.1 divided by 4, and then x transpose, which is this guy over here. Okay, and we need to bring this over here, and then we'll just take x by itself, which is this guy over here. Don't need this. Yeah, let me just bring this over a little bit more this way. Good. Now I just have to take the vector, which is this guy. This is the vector from the previous iteration. Okay. And then you subtract this by the expected output vector. So this is 1, 3.5, 9.5, 15. Okay. So when you compute all this, all right, let's see here. So when you compute this in this matrix, what will happen is I'll let you do the computation yourself. So you can certainly do this on your own. Then I'm getting really tired here. So finally, the output that you get is this becomes 1.3775, 0.8213, 0.8283, and 0.8137. and the cost associated with this particular set of parameters is 22.9365. Okay. So now the next part asks you to set lambda equal 50 and repeat the above. I'm not going to do that for you because it's just, it's just more work. It's just mechanical work. But what you finally get is get 1.3775, 0.2463, 0.2480, and 0.2432. The cost associated with these parameters, once you run it through the cost function, is 29.9295. And then you'll notice that as the regularization parameter increases, the magnitude of the parameters, except for the bias, of course, the bias actually remains the same, decreases, which is expected when you're taking a look at regularization. Okay? Alright, home stretch. And we're going to do one versus all now. Now, I'm not going to do any computations here. I'm just going to show you what the problem is. I'll show you how to set it up, and I'll give you what the final answers are. And then you can do the work yourself. Okay, here's one versus all. So suppose we have, here's the training data set that we have. Okay, so we have 3 points per class, and there's 9 points in total, so we have 3 classes. And we have 2 features. So what they want us to do is they want you to first plot these points on a Cartesian grid. Actually, okay, this is not the most up-to-date version. The most up-to-date version is on D to L, so let me just go get that quickly. Here we go. Here are the most updated points. The points that I had originally were pretty bad. So, okay. So you have these set of points, so -2, 3, 1, and -2, 4, 1, and so forth. So the first 3 points belong to the first class, the next 3 points belong to the second class, and the last 3 points belong to the third class. So the thing they want you to do is they want you to plot the points on a Cartesian grid, and you verify that for yourself that they're linearly separable. I did this on purpose. Okay, so... Okay. So we do this. So, yeah, let me just... Fine, I'll just recreate the table here. So, -2, 3, 1, -2, 4, 1, -1, 3, 1, 3, 3, 2. So, this is the first class. Second class. Third class now. Okay, so if you plot this on a nice Cartesian grid, we certainly can. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So for the first class, -2, 3 is here. Let's put it in x's, I guess. -2, 4 is up here, and -1, 3 is up here. Okay, so this is class number 1. Class number 2 is up here, so 3, 3, 4, 4. Let's just do it in circles to make it easier to differentiate. 3. So this is -4, 4, 4, 4. That's in another class, 2. And then finally we have -1, 1. Let's do triangles, -2, 0. Triangles. And finally -3, 2. Triangles. And this is another class. So we can certainly see that it's linearly separable, so it's just a matter of finding the right parameters to classify, whichever points you put in to the classifier. Okay, so what I'm going to do is I'm just going to show you how to set up the problem yourself, and then you can go ahead and do the computations yourself. But I'm just going to show you what the parameters look like. Okay, so we'll show you how to set up the problem. Then you go ahead and find parameters yourself. Okay, so recall the one versus all strategy. So how you do the one versus all strategy is that when you have a data set that consists of k distinct classes, what you're going to do is you're going to create k binary classifier parameters, one set for each class that you have. And what you do is for the ith class that you're looking at, you create a output desired y vector such that any class that belongs to the class I is set to positive, and any values or any points that are not belonging to class I belong to the negative class. And then you have k binary classifier parameters, and then what you do is you find the parameters by gradient descent, and then all you do after is when you have a new point, you just put those points in each of the classifiers and figure out which has the highest value, which states that it's the most probable class that that particular input belongs to. Okay, so recall one versus all strategy. Okay, so check k, well, not check, but create k binary classifier parameters. Assuming class I is positive and all other classes are negative. Okay, so perform gradient descent 3 times. No, perform gradient descent k times to get k parameters, k binary classifier parameters. So basically what you're going to do is you're going to obtain so there's k of these parameters, and theta I are the parameters assuming class I is positive and all other classes are negative. Okay? So you obtain all those parameters. And then to classify a new input, submit the input into each classifier and choose the class that has the largest response. Okay, because remember in logistic regression, the output, you can interpret that as the probability that the output is assumed to be the positive class. So all you have to do is just take the new input and put it through every classifier parameters that you have and choose whichever class gives you the largest response. Okay, so if you remember the update rule for logistic regression, I'm just going to state it here quickly. Okay, so let me see if I can go back and get some nice things to copy. Here, fantastic. Beautiful. This is all we need. Okay, and this here is the sigmoid function. We've talked about this already. Okay. So, what exactly do you do? So what you have to do is you have to run gradient descent. In this case, we run it 3 times. Okay? So, for class 1, what you need to do is you have to create a y vector where 1 belongs to the class that is associated with the examples from this particular class. In this case, the first 3 are all from class 1, so they're all 1s, and the rest of the vector is all 0s because these belong to classes 2 and 3 and they don't belong to class 1. So this is class 1, class 2, class 3. Okay? And then you repeat, so then for class 1 this, and then find parameters. Okay? And then you repeat this for the second class. In this case, the first class and the third class are all 0s, except for the second one. This is class 2. First class. Third class. Okay. And then you do the same thing for the third class, except that now the last 3 are all 1s, and then the first 6 are 0s. Okay. So then find parameters. This you find the parameters. And then this one you find the parameters. Okay. So I'm just going to give you what the final results are. So you're supposed to run gradient descent 3 times. Alright? So what the final output's going to be, so the after 3 iterations. Okay? It looks like this. Oh, man. So after 3 iterations, it looks like this. Okay, so this is theta 0, this is theta 1, this is theta 2, but that's assuming that this is classifying for the first class. The next set of parameters is specifically for class 2. Two, 3. Okay, so that's after 3 iterations. Now, the next part of this assignment asks you to, using the one versus all prediction scheme, determine which class each of the following input examples belong to. So you have 3 different inputs. We're going to submit this into our one versus all scheme and choose whichever classifier gives us the largest output. Okay, so now predict which class each input belongs to. Okay. So we had 2 features as we talked about before. And there are 3 examples. Okay. Now to do this is actually quite easy. Let's recall from the linear algebra lecture. If you remember, what you do is you place all the parameters. Each set of parameters is in a single column. So you make a matrix of parameters where each column is the set of parameters for a particular class. So then what you do is you take your matrix of inputs, you multiply it by this data matrix, or the parameter matrix, and then each column will give you the response of all the training examples for that particular classifier. And then what you do is you just choose which, you can choose which class each input belongs to very easily by just scanning the rows. Okay, so linear algebra lecture. Okay, so stack the parameters in a single matrix. So in this case, just take all of the binary classifier parameters and make them into a single matrix where each column is the classifiers tuned to detect that particular class. Okay, so this is for the first class, and this is for the second class. Finally, this is for the third class. And I'll show you what a plot of this looks like at the end. Third class. Okay, so all you have to do is create a data matrix of input points. So if x equals, and you have 1, 1, 1, each row is a new example we haven't seen before. Okay, so for linear regression, if you remember, if we did the data matrix times this parameter matrix, okay, what's going to happen is that you're going to get a matrix with the following properties. So this particular column are the predictions for each input using the first set of parameters. Okay, this one is the predictions using predictions for each input using the second set of parameters. Okay. Finally, this column here are the predictions for each input using the third set of parameters designed to detect instances from the third class. Okay? So then what's going to happen here is each row gives you what the predicted value or the probability would be that it belongs to each class that's defined in the columns. Okay, so this is linear regression. So for logistic regression, you just have to compute G of the whole thing, and then you're done. So for logistic regression, apply sigmoid to X of after you compute it. Okay. Okay, so when I finally do this, when I compute X of this theta here, and I compute it I compute this matrix, I get the following matrix. So 0.5411, 0.0839, 0.8465, 0.1713, 0.9875, 0.0005, 0.8123, 0.0638, 0.0231. Okay, so each row is the output probability that each row I is the output probability that input I belongs to a class. Okay, all you have to do is find the largest value, and that's the class we choose. Okay, so if you take a look at this, this is what happens when you compute the data times the data of the parameter matrix that you have, and you apply the sigmoid. So for the first example, this guy was responsible for the largest response. The second example was this guy, and the third example was this guy. So this is saying that input 1, so this is, first, second, and third set of parameters. Input 1 belongs to class 3. Input 2 belongs to class 2. So you choose whichever class corresponds to having the highest column output for each particular row. And input 3 belongs to class 1. Okay? And that's it. And here's a plot to show you everything. So the decision boundaries, I'll let you compute that on your own. All you have to do, if you want to compute the decision boundaries, is very easy. So the decision boundary here is just minus 0.5880 minus 0.6082x1 plus 0.3251 x2 equals 0, and then you solve for x2. Okay, and then you can do the same thing over here and over here as well. Okay, so you can do similar computations, and then when you find the decision boundaries, and then you plot all the points, and you can also plot the points of the test inputs so you can see where they fall. This is what it finally looks like. Okay, so we have the class 1, so this is class 1, this is class 2, and this is class 3. Probably shouldn't have moved that, I apologize. But and then these are the different test points, And then these are the decision boundaries that for each particular class. So this blue line is the decision boundary that separates between the points that are from class 1 with the rest of the points. This green line is the decision boundary that classifies between class 2 and the rest of the points, and the red line separates between the green is 3 and the red is 2. So when we plot the test points together in tandem with all these other training points, sorry about that. So when you plot all of these test points together with the training points, you'll see that you expect these test points to belong to the class that's within the vicinity of these, and yeah, you do expect that they do match. Okay. So I'm going to do a brief stint in classification accuracy, and then we're going to go on to Bayesian decision theory, and then we're going to call it quits. Man, this is a long review. I hope you guys appreciate it. Okay, let's do classification accuracy. Classification accuracy. Here. Okay, so the whole purpose of classification accuracy is to be able to assess whether your predicted or your binary classifier is able to predict labels properly. Okay, so basically what's happening here is, suppose we have a binary classifier that we've obtained the parameters for, and these are the most optimal after you perform gradient descent. And the best way to figure out whether or not your classifier is accurate is to take the same data points that you use to train your model or to figure out the parameters, and see whether or not each of those inputs can correctly be classified and compared with your expected classes. So all you have to do is you just have to add up how many of those points were classified correctly. And you just find the fraction of those and you multiply by 100, and that would be your classification accuracy. Okay, so we have this example here, and they want us to figure out what the classification accuracy, given the fact that the predicted labels or the predicted classes are what our binary classifier classified these points would be, but the expected labels are what the true labels are. Okay, so classification accuracy. Okay, so we have the following table. So do I have it? Yeah, I do. So you can think of these as the predicted classes. Okay, so suppose we have a binary classifier, and we found the optimal parameters, and suppose we have a test data set with the expected labels, and then we use the data set and submit the examples through the classifier, and we get the predicted labels of the classes. And how do you assess the accuracy of the system? All you have to do is just calculate a fraction of examples that were classified correct when you compare it with the expected labels. Okay, so let's write this down. So suppose we have a binary classifier and found the optimal parameters. Okay. Now, suppose we have a test data set with expected labels or classes. Okay, so we use the data set and submit the examples through the classifier. And we get the predicted labels or classes. Okay, so how do we assess accuracy? How do we assess the accuracy? Well, it's quite simple. If you remember from class, all you're doing is you just find the fraction of classes that match between the expected and true classes. Sorry, expected and predicted classes. Okay. Then multiply by 100. Okay. So for this example, right, suppose we had a test data set and we, and we know what the expected classes are, and we submit it through our binary prediction scheme, and we get the following set of predicted labels, and these were the expected labels. So all you have to do is just add up how many of them matched. So these matched, these matched, these matched, and these matched. And these matched as well. So 5 out of 9 matched. Okay? So therefore, above example is simply 100 divided by 9 times 5, 55.55%. Okay? So that's pretty bad. I wouldn't say that's a very good classifier. So you probably won't want to retrain it again and do something different. Okay? Now this one is easy as well. This is basically considering when you have multiple labels. So this is when we have 4 classes. So the way that you compute the classifier accuracy is essentially the same. It's just you have multiple labels now. So all you have to do is just figure out which labels matched. In this case, we only have this guy and this guy. So that's pretty bad. So the classifier accuracy in this case is simply 100. Well, there's 9 examples, okay, times 2, which is 22.22%, which is pretty bad. Okay. There has to be some push and pull here, because if you have 100% accuracy, you're probably overfitting, and it probably won't generalize to new data points. So you want to have it as high as possible, but not perfect as 100%, because it just won't generalize. Okay? Alright, let's end off with Bayesian decision theory, and I'm going to call it a night. Okay, so Bayesian decision theory. So I'm just going to skip right to the last 2 questions. So let's say we've got a binary classifier. Okay, so we want to classify between 2 different classes, and we're only using one feature. One feature will be what is going to discriminate between the 2 classes. And the underlying assumption is that the features are randomly distributed. They have a random distribution, but they follow under a Gaussian distribution. Okay, so we're going to basically walk through Bayesian decision theory step by step. So the first thing you need to do is you have to compute what's known as the prior probabilities. And what the prior probabilities are is just simply the fraction of inputs that belong to each class. Alright? So all you have to do is just add up how many inputs belong to which class. In this case, for class 1, omega 1 is the notation, there's 1, 4, and then 5, and then there's 10 examples. So the fraction is just 5 over 10 or 1 over 2. And the remaining is 5 for the other class, and that prior probability is also 5 over 10 or 1 over 2 as well. Okay, so we're going to compute that first. So hopefully I've got a table here. Yeah, I do. Okay, so Bayesian decision theory. So the first thing we need to do is compute prior probabilities. Okay? So it's simply fraction of features belonging to each class. Okay? So we have 1, 2, 3, 4, 5, and then 1, 2, 3, 4, 5. Okay? So the prior probability for the first class is simply 1 over 2. The prior probability for the second class is also 1 over 2 as well, because there are 10 inputs, each of them are 5, so of course they're equal. Okay? The next part that you have to do is you have to compute the mean and standard deviation. And not the standard, the variance for the features of each class. Okay? So I'll just show you an example of how to do it for the first class, and then you can do it for the second class by yourself. So if you compute the mean for the first class, you just have to go through each of the examples and segregate which of them belong to the first class, which belong to the second class, and then you add up the mean, add up the features for that particular class. So for the first class, you have these 5 points, 1, 2, 3, 4, and then 5. So you have 0.5377 plus or minus 0.2588, okay, plus 0.3188, plus 0.3426, finally plus 3.5784. Divide that by 5. So that's the mean. Oh, man. Okay, and this is equal to 0.60766. Okay, the variance is simply just the square of the standard deviation. So 5 minus 1. 0.5377 minus 0.60766 squared, okay, plus minus 2.2588 minus 0.66766 squared, okay, plus 0.8622 minus 0.60766 squared, plus 0.3188 minus 0.66766 squared. Well, not 6, it's 0. Okay, squared. And finally, the last one, 3.5784 minus 0.60766 squared. When you compute this, we get 4.2988. And then I'll let you do the other ones on your own, so you can, have some practice. And this is 46684, 2.986, 2.9896. Okay. All right. So now what we have to do next is we have to compute the decision boundary. The decision boundary is the point where you decide whether or not one class belongs to one or another. All right? So, okay, so we have to compute the decision boundary. So, if you remember from class, the discriminant function it's when the discriminant function for the first class is equal to the second class. Okay, so if you remember from class, the discriminant function it's equal to log the posterior probabilities. Yes. Conditional. Okay, and then we can also split this up. Oops. Okay, and this guy here is what's known as the likelihood or the class conditional probability. Okay, and it follows a Gaussian distribution. So it looks like this. Okay, this is just for one feature. So now, if I take the log of this, I'll let you figure this out yourself, but basically it becomes it's just using log rules and properties. Okay, now we can eliminate this term because when we set both of these equal to each other, you can remove it on both sides. So constant appears on both sides. Okay, so finally you basically just have to set these two equal to each other, and then we're good to go. So therefore, the decision boundary is equal to constant. So then you have to add the log probability of that class. Okay, so all you have to do is just set them equal to each other. And that's the decision boundary. Okay, so all you have to do now is just take the means and variances for each of the classes and you just substitute them in. Okay, and also the prior probabilities as well. That's just equal to a half each. So therefore, you just set them equal to each other. So this is okay. Okay, so that's what the decision boundary would be. And then all you have to do is just substitute, you know, your mean and standard deviation. So this was 0.60766. This was 4.2988. This was 2.9896. This is 4.2988. 2.9896. And then this is a half, and this is a half. So you can cancel these out because they're both constants. They both appear on both sides. So when you solve for this is a quadratic equation. What will happen is that you get the following quadratic formula. Okay? So when you solve for this, okay, you can use the quadratic formula if you wish, right? When you solve for this, you get x minus 0.5755 and x plus 6.4168. Now you have to decide which one makes sense. If you take a look at the distribution of the features that we have, you'll notice that the smallest value is equal to minus 2.76. And now if you take a look at the bottom over here, you'll see that the solutions are 0.5755 and minus 6.4168. So this seems rather extreme. This is way beyond any of the features that we have. So this is a extreme point. So ignore it. Okay? So this would be the final value that you have. Okay? So basically, the Bayesian decision rule is just gonna, you just have to choose which one is larger. Okay? So if, okay, so what we actually did here, okay, is G1 and then G2. So what I did here was I created this by doing G1 minus G2. Okay, so if G1 is greater than G2, or if G1 minus G2 is greater than 0, this is your Bayesian decision rule. Okay, so this is the Bayesian decision rule. You choose the one that has the higher probability. Okay, so if you take a look at the question here, you compute the decision boundary. That's what we did, and then what you have to do now is, given these inputs, figure out what class each of them belong to. Well, that's really simple, right? All you have to do is just figure out which values are going to satisfy the inequality. So in this case, if x is greater than 0.5755, decide the first class, else decide the second class. Well, that's pretty simple. So if we have x, this is our class, minus 2, minus 1, 0, 1, 2, and we decide if it's bigger than 0.75755, well, this is the second class, second class, second class, first class, and first class. Right, because 1 and 2 are bigger than 0.5755. Okay? Now we're going to do two-dimensional, and then we're going to call it quits. All right? So when we have two features now, what's going to happen is that we have to consider the multivariate definition. Okay, so the Bayesian decision rule is exactly the same, but we just have to be a little smart in the way we compute things. Okay, so the next question. You have two features now. Okay, so suppose we already have the prior probabilities okay, the means and covariance matrices. I'll talk about covariance matrices in a little bit of the features. Okay, we also assume that Gaussian distributeds also assume Gaussian distributed. Okay. Also, it's usually the case where the covariance matrix is shared between two classes. So, covariance matrix. is shared between the two classes. Okay. Also, we know that the prior probabilities are the same. That's given in the problem. Okay. And we also know that the mean feature vectors are -1 and 1 for the first class, and +1 and 1 for the second class. Okay, so this is class 1, and this is feature 1 mean. This is feature 2 mean. Okay, and this is the same thing for class 2. Okay. And then also we have the covariance matrix. This is given in the problem. Okay, so this is sigma 1 squared, sigma 1 2, sigma 2 1, sigma 2 squared. Okay, so if you recall what the covariance was, so recall covariance definition. If you recall the covariance definition, X okay, sorry, this is J. So you're finding, this is what's defined as the covariance. So you're summing over sum of differences between the products between the feature I and feature J for every example K subtracted by the mean. Okay, so this is covariance. And then the variance is pretty much the same. It's just sum of square differences. Okay, this is variance definition. Okay. All right. So the Bayesian decision rule is pretty much the same. So you have to remember what the class conditional probabilities are. So for the Bayesian, for the multivariate is equal to okay. So n is that this is the total number of features. Okay. This is the determinant of the covariance matrix. Okay. And this is the inverse. Okay, so once we have this established, the Bayesian decision rule is quite, it's the same. So let's take the log. Okay, to be sure. We know, once we compute this, so I'll let you figure this out on your own, but when you apply the log to this, it's simply equal to and then minus okay, So because the covariance matrices are shared, these two constants, you can remove them because they're up here on both sides. Can remove. Okay, so finally, the discriminant rule is very simply this. Okay, that is the discriminant rule. Okay, so for 2x2 matrices, the following properties will probably be helpful. Okay, so let's say A consisted of A, B, C, and D. Okay, so when we do this, if we find the determinant, simply AD minus BC. And if we find the inverse, simply 1 over the determinant times the adjoint. So you flip the top left and lower right corners, and then you negate the other two. Okay? And then for diagonal matrices, that's when only the diagonal components exist. So something like A, B, 0, 0. Okay? The determinant is simply AB, and the inverse is just another diagonal matrix where the diagonals are just 1 over the coefficients. Okay? Okay. So now we've got this. All you have to do is just calculate what the decision boundaries are. So first we are given a covariance matrix of 2, 2. And what that means is that the features are independent. They don't correlate with each other. So therefore, let's do the first one. Okay, so this is a row vector. Minus, and then this is the first mean. Take the inverse, this guy, and then this is a column vector now. Okay, and then you set this equal to same thing. And this time the means are positive. Covariance matrices are the same. And then finally we do the same thing for the other class. Okay. So when you compute this, right, so you can get rid of these. This becomes a half and a half, a half and a half. Okay, so when you're doing this matrix multiplication, what's going to happen is that you have a minus half here, and then this here, this vector becomes x1 minus 1, and then this is x2 minus 1. Okay. And then this is a column vector, x1 minus 1, x2 minus 1. Okay, this becomes x1 plus 1, x2 minus 1. This becomes x1 plus 1, x2 minus 1. Okay, so when you actually go ahead and compute this matrix multiplication, what's going to happen is when you work this out, okay, this, I'll let you know, this will be an exercise for you. You can go ahead and do this. But what will happen is that you finally get the following left and right hand sides. Okay, and you'll see that this cancels with this, and the only way for this to be satisfied is if x of 1 is equal to 0, and x of 2 can be anything. So therefore, x of 1 equals 0. Right? Because this is the only way that you can satisfy this equation. You can expand it out, and you can solve for x, but x of 1 is equal to 0 is the only way that this can be satisfied. Okay? And then the next part is to repeat for... Okay? And then you're going to see that this is still x1 equals 0 when you go ahead and solve for that. And finally, you're going to repeat for... This is what happens when you introduce covariance into the features. And then when you solve for this, what's going to happen is that you're going to get x2 equals 3 over 4 x1 plus 1 over 4. And that's it. So that's the decision boundaries for the two features. Okay. So that is it for the review. Hopefully this was fruitful. I'm pretty tired, so I'm going to go to bed. But I'll hopefully this will be enough review for you to be able to pass the midterm. So good luck, and I'll see you in a couple of weeks.